Okay, ladies and gentlemen, this is where we left off, and we were talking about all of these alcohol reactions that are just swamping us. I mean, we're really sinking in the alcohol reactions at this point, and there's still more to come. All right, so the question I always get, and I really haven't mentioned this yet, is why? I mean, ROH, it's a good nucleophile. Why do we go through all of this trouble just to get the OH off and replace it with a bromine? And this is an alkyl halide, and we normally don't do anything with alkyl halides. We use them to make other things. So why do we have to go through all of this? Why can't we just go straight to the alcohol or to the alkyl halide step and skip the alcohol group and just order the alkyl halide and send it to the lab and use that as a starting point? Okay, well, here's the reason that we do it. A lot of times we use these alcohols, we protonate them, give them black eyes, make them leave, and then we replace that with a halogen, and then that halogen can be used to make multiple things with, because these are bromines and chlorines and they're very good leaving groups. Pretty much everything's going to beat them out with the exception of a few. So again, the question, why don't we just start here? I mean, why do we even want to fool with this? Why do I need to go into a lab and protonate the alcohol with acid, or use this pyridine and phosphorus trihalide, or use the pyridine and the phenyl chloride? Why? Well, folks, I want you to think of high school. I want you to think of a high school date. I want you to think of a high school date at the Taco Bell. It's cheap and easy. And alcohol reactions are cheap and they're easy. That's why we do them. If you take a look at the cost of an alcohol, and you take a look at the cost of the acid maybe that you would use in that reaction, these are very, very cheap and easy to come by. All day long, we typically have them in the lab already, but all day long I can order, and come out at fractions of the cost than if I just ordered the alkyl halides. These things are a little bit more money. So if I'm looking at budget, if I'm looking at something cheap, if I want to save cost, then this is why we do the alcohol reactions the way that we do them. I take the cheap alcohol, I take the cheap acid, we go to Taco Bell together. It's a very easy date to plan, and folks, within a matter of a few minutes, I've got an alkyl halide that I want. That's why we do it. So that's why we go through this discussion of the reactions of the alcohols to make the halogens, and then turn around and do the halogens the same way that we've always done them, replace the bromines and the chlorines with groups that we actually want. That's why that process goes forward. All right. So we have another reaction that we can use in order to help us out here. And this is going to be called a sulfonate, sulfonate, ester. So this is just another way to make an alcohol group active. We activate the alcohol group. We make it a very good leaving group so something else can come on in its place. Now, before we go forward, I want to go back and I want to talk about this term ester. What is an ester? For some of you, it might be the first time that you've seen this. This is not an ether. Ethers and esters are different. Be careful. And a lot of times, Chem 251 does not introduce an ester. And the reason is because it will be introduced in Chem 252 later on at the end of the semester when we talk about carbonyls. So a ester group is basically a carbon that's a double bond O. There's my carbonyl. That's what we call that, a carbonyl, with an oxygen. And we probably have something random over here, and we probably have something random over there, but that piece in the center, C double bond OO, that is an ester group. Now, the other thing I want to say is that for some reason, people confuse sulfonate esters with thionyl chlorides. And maybe I shouldn't have even mentioned it. But these two things are not the same, folks. And I think the reason is because sulfonate, this includes sulfur, right? And thionyl, thio was in reference to sulfur. So this also has sulfur. And I think that's where the confusion lies. But folks, they are not the same type of compound. They are different. So pay attention. Make sure that you're using and thinking of the right thing, because those two things are always a point of confusion for people, especially in the very beginning. But here's the honest answer. It doesn't really matter. And the reason is because we're using a sulfonate ester for the same purpose that we're using a thionyl chloride. We're making an alcohol group ugly. We're making it leave, and a halogen is going to go on. All right, but sulfonate esters do something a little different. I mean, that's why we talk about them. But the overall scheme here, this is kind of what goes on. So let's talk about sulfonyl esters. What goes on? Okay, well, you have an alcohol group. It doesn't really matter what it is. ROH. That alcohol group, bam, we'll have to make it ugly. We'll have to get it to leave. Well, one of the ways that we can do this is using a sulfonate ester. All right, well, a sulfonate ester is like an ester, but instead of a carbon, there's sulfur. Oh, go figure, right? S double bond O. But it doesn't have one, it actually has two. And you can kind of think of this as my C double bond OO, but it's an S double bond O double bond O. Okay. And then off of here, we have a chlorine, and then we have just some kind of random alkyl group. This is something in particular that we will call a sulfonyl chloride. And you're going to see this make a sulfonate ester full blown in just a second. So just bear with me. So we use something like a sulfonyl chloride, and we have to put it in, guess what, a solvent. And what do you think that solvent's going to be? It's going to be pyridine, for the same reason that we've always used it, really. And what happens here is that this R and O from the alcohol stays put, and this chlorine is going to be kicked off, and sulfur is going to go on there instead. And this is really the true blue full shebang sulfonate ester. And you can see how that gets generated now. The S double bond O with that O group that is present. Okay, well, here's the thing. Once those sulfonate esters form, folks, these are very good leaving groups. They are ugly, just like some of the other groups that we've talked about before. So that group can leave, and a halogen can go on and replace it. All right, so now, before I go any further, there's a couple of sulfonyl chlorides that are commonly used throughout this process in order to make those sulfonate esters with. S double bond O with a chlorine, and sometimes we'll use this ring system. And this ring system is a double, single, double, single, double, so delocalized, with a CH3 group. And then sometimes we'll use a sulfur, double bond O with the chlorine, and then we have a methyl group that might be here instead. And then sometimes we'll use a sulfur, double bond O with a chlorine, and we have a carbon with 3 fluorines. I know. It's kind of strange to see fluorine out there, right? So these are 3 common sulfonyl chlorides that we can use throughout this process. Each one of these has a name, and here's what they're called. This middle one down here, this is going to be called methane because I see the CH3 group that's there. And the rest of it, sulfonyl chloride. Go figure. All right. This one down here at the bottom with the fluorines. Let's look at that one. This is going to be called trifluoro. Why do you think? Oh, because there's 3 fluorines. Methane, because there's 1 carbon. And then the word sulfonyl chloride. Well, look at there. The one up here at the top, though, this is the most common. It's the most common because of that ring. I mean, we like to use that ring because it improves the stability of that piece of molecule. So this molecule feels really good about itself. I mean, it might be ugly. Eventually, it might be ugly. But, you know, it feels good about the way it looks. And sometimes it's all that matters. It's all about self-esteem. And that molecule has plenty of it. What do we call it? Okay, do you see the position on the ring? They're directly across from each other. That S double bond O Cl is directly across from the CH3. Well, that position is called the para position. So this is going to be called para. This ring with a CH3 group like this, the benzene with the methyl, is called toluene. That's its common name that it goes by. And then we add on the word sulfonyl chloride. Para-toluene sulfonyl chloride is really all one word. I just ran out of room. But it's the most common. And because it's the most common, we have an abbreviation for that one. And this is going to be TSCL. Tosyl chloride. So I don't know about you, but I don't want to write that para-toluene sulfonyl chloride every time that I have to use it in a reaction. So TSCL is representative of that para-toluene sulfonyl chloride. It's called tosyl chloride, and it refers to that same structure up there at the very top. But depending on how tricky these questions want to be, they could give you typically 3 versions of a sulfonyl chloride, and they all perform the same way. They all do the same thing. No difference in them. Now, here's the ingredient. We know the other ingredient is our alcohol group. And now we want to talk about what kind of product, what kind of cake is going to get formed for us. Well, I told you these sulfonyl or sulfonate esters, they're pretty ugly. And the reason that they're ugly is because, you know, carbon doesn't want them. They're very good leaving groups. They feel really good about themselves. So here's what kind of happens. Let's say that we have a CH3, CH2, CH2, CH2OH. And we react this with tosyl chloride. And we need pyridine in order for this to work out. What goes on? Well, I can do the shortcut way. I can say, oh, okay, well, this OH group, bam, we make it ugly. This OH group kind of leaves, and what we have in its place is this tosyl chlorate kind of stuff. So CH3, CH2, 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 and the oxygen's there with the tosyl. Okay, well, I'm using abbreviations here. We'll go back and we'll fix this in just a minute. But I'm just using simple abbreviations. And then from this point, this piece, folks, it's a very good leaving group. This is my sulfonate ester here. Sulfonate esters are great leaving groups, and the only thing that I have to do at this point is just come in and give it whatever piece that I want to give it. So let's say that I want to maybe throw in, who knows, like a SCH3. I don't know, I just made that up. Well, that group will come in, boink, off it goes. OTS goes away, and what we end up with is a CH3, CH2, CH2, CH2 with my S and my CH3 group in it. All right, so there you go. That's how this alcohol reaction works. Okay, well, let's say that I want to do something else. Instead of the SCH3 group here, let's say that I want to bring in, at that point, a C triple bond N. That's a nucleophile as well. That nucleophile comes into the bar, carbon looks at that oxygen and goes, ew, I don't like you, and I want the C triple bond N instead. So this SCH3 gets erased, and what we put on here is a C triple bond N. It is just another substitution reaction. That's all that we've been doing with these alcohols. That's it. It's the same stuff over and over and over. We're just using different ingredients in order to get there. Now, here's the thing. I told you that we're using abbreviations, but let's kind of draw out the real thing. Okay, tosyl chloride. Keep in mind what that structure is. So what we end up with here is a CH2, CH3, CH2, 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 oxygen, this sulfur double bond O with this ring structure that's delocalized and a methyl group. That's what this tosyl group is, right here. So now you can see why we use abbreviations a lot of times for this. This is a very big molecule. It takes a lot of effort to write down on a sheet of paper. No one really wants to do it, so they just abbreviate it with a TS and they go on about their business. You need to realize that that TS is not an element from the periodic chart. You're not going to find a TS on there. And that TS is representative of that para-toluene sulfonyl chloride. So this is the ester, the sulfonate ester, and this is the very good leaving group because, look, why is it a good leaving group? We've got delocalization here. Molecule feels really good. We also can get the delocalization to go up and out into the oxygens that are here as well, because that is a double single and then it gets into the ring system. So the delocalized system can spread throughout the entire molecule pretty much here. And that molecule is very good on its own. It's Mr. Mrs. Independent. It doesn't need anything with it. It might be ugly, but folks, it's perfectly okay by itself. It can carry that negative charge when it breaks away. It can carry that negative charge without a problem. And that is why we use this the most often out of all of the sulfonyl chlorides that are out there. That para-toluene sulfonyl chloride, the methane sulfonyl chloride, and the trifluoromethane sulfonyl chloride. This one simply is the best out of the three. All right, so here's the overall picture. My alcohol gets reacted with my tosyl chloride. It forms the sulfonate ester, and then that forms a good leaving group that I can then use that and replace it with whatever kind of group that I want it to be there. A couple of pieces of terminology here that I want to talk about. The first piece of terminology is this thing here, that whole piece. This is an alkyl group, right? CH3, CH2, CH2, CH2. And in organic, we often write organics that are alkyl groups with a random, it can be anything it wants to be, as an R. All right, so there's my R. And then I see the oxygen that's right here. So that oxygen is going to be representative in the abbreviation there. And then this piece we said was tosyl, right? This is my tosyl group. So that's going to be a T. So very often we call these rots. My alcohol reacts with tosyl chloride to make a rot. And that R means a random alkyl group in front. It can be anything it wants to be. 3 carbons, 2 carbons, longer carbon chain with a ring on it. I don't really care. It's just a random alkyl group. We call that a rot. So my alcohols react with tosyl chloride to make a rot, and that rot will basically break apart. The leaving group leaves, allowing me to put on whatever kind of nucleophile that I want to put on at that point in time. Now, let's take a look at mechanism. I know. Oh, gosh, here's the mechanism again. What's he doing to me? We're just going to have to bear through it. So I first want to start off with the sulfonyl chlorides. My S double bond O with the Cl. And just this random alkyl group that might be there, right? This could be my benzene ring with a methyl. It could just be a methyl group. It could be that trifluoromethane group. Just anything random. Okay, they all work the same way. And I have this OH group for an alcohol. Okay, so we know that something has to happen here. And we've already kind of talked about it. So the oxygen's got a free set of electrons. That makes this partial negative. The sulfur is getting pulled in all directions. It makes that a partial positive. And as far as the first step of the mechanism goes, I can keep or start my arrow there at my negative source, and I draw it to the more positive piece. Well, that sulfur said, okay, now I'm way overloaded. And I think it's important to mention here, look at the sulfur. It does not abide by the octet rule. Not everything does. That's a lie that general chemistry told you. And probably a lie that I told you in chemistry 251, trying to make you believe that everything had the octet. It does not. It does not have to. There's atoms that are out there that are perfectly okay with more than 8. And sulfur is one of these. Look at it. Look how many bonds it has. So this sulfur cannot take another bond, though. I mean, this is it. So it's got to say, okay, which one's the ugliest out of this group? And it's got to be you, chlorine. Poof, off you go. And that chlorine says, fine. I wanted these electrons anyway. I mean, I was mooching off of you as much as possible, so I'm going to mooch off of you one last time, and I'm going to take your electrons, and away we go. So what we end up here with now is this RO from the alcohol, the sulfur, with a double bond O, and just some kind of other random alkyl group that's out there. Again, tosyl chloride is okay. The methane sulfonyl chloride's okay. It doesn't really matter what's there. We're just looking at mechanism, and it's all about this centerpiece that I'm drawing right now. Well, we said we need pyridine, right? So this pyridine structure, you got to keep in mind that oxygen still has the hydrogen. It hasn't lost that H from that oxygen yet. So it's still there, which also means that this oxygen's a positive charge at this point, and this oxygen's way out of line, and it needs to get rid of something, and hydrogen's very disposable. So I need pyridine in order to get that job finished. So pyridine's going to come in. It's going to attack the hydrogen. It's going to rip it off. And that oxygen sucks those electrons up from the hydrogen bond in order to make that a neutral atom again. So what we end up with this time is an R with now an oxygen that's not charged. It's perfectly happy with a sulfur, double bond O, and some kind of other random alkyl group that I want to put on that side of the tosyl or of the sulfonyl chlorides. Well, we still have the chlorine that's out there as well. It's one of the reasons that we use pyridine, because again, that chlorine could come in and it could grab that hydrogen if it wants to make HCl. And now rearrangement happens, and that's the whole point of using a sulfonyl chloride, to prevent rearrangement from happening. So this is going to give me my rot right here. My alkyl, oxygen, tosyl. If this R group is a benzene ring with a methyl group. Okay? So this piece is a very good leaving group. So therefore, if I added something like my cyanide that I used before in that last example, That piece can come in and it goes, oh, look, this is a really ugly partner for that carbon. So, hey, carbon, you want to hang out for a little bit? And that carbon says, yeah, absolutely. Go away, oxygen. I don't want you. And that piece says, okay, fine, I don't need you either. And off it goes. So that piece of the mechanism will end us up with an R and a C triple bond N that has replaced my alkyl group. That's how the mechanism has worked. Those are the steps that make this process go on. Now, let's talk about some things. There's some caveats here. First off, we're talking about substitution quite a bit, aren't we? We're talking about the substitution of the leaving group with another nucleophile, substitution playing a really big role in this particular type of reaction, as it has really with some of the others as well. But the substitution reactions will not happen if you have an alcohol that is tertiary. It's too sterically hindered. Sterically hindered means there's too many buddies that have went to the bar with it. And those buddies are looking out for that carbon. And it's going to prevent things from coming in and reacting with it. It's like bodyguards. So tertiary alcohols will be a problem, and that problem is that they're too sterically hindered in order for these substitution reactions to take place. In addition, something else I want to say, the tosyl chlorides. I told you that they're pretty ugly, right? Well, these things are 100 times uglier than chlorine. That means they are 100 times better as a leaving group than chlorine is. So you can imagine that tosyl does want to go away. If it sees an opening, carbon's going to kick it to the curb as lickety-split as possible. And something else is going to come on into that position. Even a halogen, even a chlorine will come on and replace that tosyl because chlorine is 100 times prettier than the tosyl group is. Something else I want to say before I stop this video is stereochemistry. Oh gosh, stereochemistry. I hate stereochemistry. Do you hate stereochemistry? Well, here's the thing. You know, we've talked about tosyl chloride now, and it really looks like this is an alcohol, and the alcohol is converted over to this tosyl chloride piece. And then what happens there is that tosyl chloride piece gets replaced with some type of nucleophile. And this requires a substitution reaction, but it's going to be a substitution reaction that has to involve a carbon as a cheater. So we see one flip here as far as stereochemistry goes. So what that means is that if you had, let's say, a carbon with a methyl group, and let's say a hydrogen here dashed, and a solid wedge here with an OH, and an R group there. Just some kind of random R group, it doesn't matter. And we react this stuff with tosyl chloride and pyridine with maybe OCH3 as the nucleophile that will go in and replace it. It's one inversion step. Okay, so here's my alcohol group. That alcohol group will eventually get, that oxygen kind of stays there, right? That will eventually get the tosyl group. That's a very good leaving group now. And now we add on our nucleophile that will replace that piece. But when we do, this bond is going to be affected. So Walden inversion is going to happen here. I flip the stereochemistry. So one flip, and if this is R, it goes to S. If that is S, it goes to R. So now what I need to show is over here on this side, I'll kind of keep everything the same, just so you can see that. So this OTS is going to get replaced with my OCH3. I mean, that's what goes on. It's a substitution reaction. Notice I didn't do anything to my bonds yet. But in my head, I know that if we do want to talk about stereochemistry, these tosyl chlorides happen really in one step, and that's it. So carbon comes through the back, or carbon opens up the back door, allows this nucleophile to come in and replace the tosyl chloride or the tosylate. But because it came through the back door, folks, you got to keep in mind that the stereochemistry will actually change as well. All right, so if I'm going to keep my solid wedge, I shouldn't have deleted that. So what I'll do is that I'll erase the hydrogen and I'll erase my OCH3 group and I'll just switch those out. That makes sure that it does flip on me, okay? The other ones that we've talked about, not so much. They don't really happen that way, such as PBr3 with some pyridine. And let's say OCH3 gets added on here as the group that's going to get replaced. All right, so if I take this CH3 group, R, OH, hydrogen, let's think about this mechanism. The OH is going to get replaced, and that gets replaced by a bromine in this case. And then that bromine is going to get replaced by an OCH3 group. Okay, there's two steps there. Notice what I did. The OH leaves, the bromine goes on. That's a complete flip. So there's our first flip. That's our first Walden inversion. And then in the next step, bromine's going to get replaced. And then bromine is going to get replaced by OCH3, which means another backdoor reaction has to happen. So it flips again. We get two Walden inversions that go on. I know what you're thinking. Oh my God, what's he talking about? I don't know what he's talking about. I'll just write it down and I'll just worry about it later. Okay, so OCH3 group and hydrogen. So with my PBr3s, my PCl3s, the tosyls that we've looked at before, or the thios that we've looked at before, those happen in two steps. And because they happen in two steps, there's two Walden inversions, so the stereochemistry stays the same. That's the take-home message here. Stereochemistry stays the same as what it was in the very beginning. I don't have to flip bonds. I don't have to flip R's and S's and so forth. In the first round, this tosyl chloride stuff, it doesn't really happen the same way. It's a different type of mechanism. So this is a one-step mechanism. So therefore, the stereochemistry will flip. And if it starts out as R, it will go to S. If it starts out as S, it will go to R. And notice what I've done to the bonds. I've flipped the positions of the bonds around. So this is one of the things that we have to keep in mind as far as the tosyl goes, because this is what happens with every single one of them. Not just with the benzene ring and the methyl group. Any of those sulfonyl chlorides will do this. It will only flip once before my new incoming nucleophile goes in. The others, though, that we've mentioned, that we've talked about, it's a two-stepper process. So an SN2 happens first, and then another SN2 happens again, and that flips the first time, but then it flips back to the original position in the second time. So this is just something that we're going to deal with just a little bit to kind of think about what goes on as far as stereochemistry goes, in addition to substituting these groups out and getting these alcohol reactions to go forward. So here is an example problem I'm going to leave you with. Here's A, B, C, and D. Notice in each one of these cases, we have an alcohol group, and that alcohol group is going to get replaced by something. We're going to activate it, and we're going to go through the different options that we've talked about so far. So in A, it's my phosphorus trihalide. In B, it's my hydrobromic acid. In C, it's my thionyl chloride. And then in D, it's a tosyl chloride. So how do these things differ, not only in product side, but how do they differ in stereochemistry as well? So these are the questions that we're going to work through in the next video. Try a stab at them. Maybe if you're uncomfortable with stereoisomer, just don't even worry about the stereoisomers right now. But you can at least predict a product and know what happens to that alcohol group in the very end of this process. So at least attempt that. If you want to leave stereoisomers off, leave them off, and we'll deal with that when you get back. But can you predict the overall product? That's the bigger question. So this is where we'll pick up in the next video, and I'll see you then.